Before getting into irrationals, let's quickly review rationals, which are numbers that can be written as an integer divided by another integer. So which of the numbers down here are rationals? Select all that apply. Right, all three of these are rational numbers. 13/5 is already expressed as the quotient of integers, 13 divided by 5. 0.71 is the same as 71 divided by 100, and 0.6666 and so on is the same as 2 divided by 3. So all three of these numbers are rational. So then what are irrational numbers? They're all the numbers that cannot be written as one integer divided by another. You might already know a few famous examples. Pi, the ratio between a circle's circumference and its diameter, is irrational. Pi equals about 3.14159 and so on, but it turns out there's no way to write it as a fraction with integers. The same goes for Euler's number, commonly represented by the letter e. It equals about 2.71828 and so on, but there's no way to write e as a fraction either. In this lesson, we'll take a closer look at another irrational, the square root of 2. First off, use the calculator to express the square root of 2 to at least 2 decimal places. Excellent! So the square root of 2 is approximately 1.41421 and so on. So in this lesson, we'll prove to ourselves that the square root of 2 is irrational. So where can we start? Well, imagine the square root of 2 was a rational number. If that were the case, then you could write it as a fraction a over b, where a and b are both integers. That's what it means for a number to be rational, right? It means you can write it as a quotient of integers. Okay, great. Let's take a closer look at this equation. We can get rid of the square root over here by squaring both sides. So on the right, we can distribute the square onto the a and the b inside the parentheses, giving us a squared over b squared. Can you simplify the left side of this equation? What's the square root of 2 squared? Exactly, so the left side of this equation is 2. Okay, so if the square root of 2 is a rational number, then we should be able to find integer solutions a and b to this equation. Let's simplify this a little more and multiply both sides by b squared. So the b squared over here cancels out the b squared in the denominator, leaving us with a squared on the right. Okay, so our equation now reads 2 times b squared equals a squared. Can you find any positive integers a and b that satisfy this equation? Yeah, there are no positive integer solutions to this equation. So why is that? Well, let's look at a few square numbers, like 36, 49, and 64. The trick here is to write out each square's prime factorization. So 36 equals 2 times 2 times 3 times 3. We've written it as the product of prime numbers. 49 equals 7 times 7, and 64 equals 2 times 2 times 2 times 2 times 2 times 2. So that's 6 2's. Looking at these factorizations, what do you notice? For square numbers, the prime factors always come in pairs. 36 has a pair of 2's and a pair of 3's. 49 has a pair of 7's, and 64 has 1, 2, 3 pairs of 2's. Why is that? Well, because the factors come in pairs, that means we can split the pairs to form two identical groups. Over here we have 2 times 3 and then another 2 times 3. Because you're multiplying 2 times 3, or 6, by itself, that's what makes this a square number, right? Take a look at 64. It's 2 times 2 times 2, or 8, then times another 2 times 2 times 2, or 8. So prime factors of squares always come in pairs. Alright, let's return to our equation up here, which says if you take b squared and multiply it by 2, you should get a squared. Well, because b squared is a square number, that means all its factors come in pairs, including any factors of 2. And now we're multiplying b squared by another 2. Well, this 2 has no pair. So 2 times b squared, which equals a squared, has an unpaired factor of 2. That means it can't be a square number at all. Yikes! So it turns out there are no positive integers a and b that solve this equation. And that means our original equation, the square root of 2 equals a over b, also has no integer solutions. In other words, the square root of 2 is an irrational number. It can't be written as a quotient of integers. Now, there are many irrational numbers. Now that you know the square root of 2 is irrational, see if you can prove to yourself that the square root of 2 plus 1 is another irrational expression. The same goes for the square root of 5. And knowing that pi is irrational, see if you can prove that 2 pi is also irrational. As you'll discover, there are infinitely many irrational numbers out there. Real numbers are all the numbers on the number line. So any number that falls on the number line somewhere is called real. The set of real numbers includes all the integers, and it also includes all the rationals. Of these expressions here, which is a rational number? Exactly, so -9/7 is the only rational here. It can be written as one integer, -9, divided by another integer, 7. 3 divided by 0 is also one integer divided by another, but dividing by 0 gives you a result that's undefined. It's not a number at all. The set of real numbers also includes all the irrationals, all the numbers on the number line that can't be written as the quotient of integers. So, of the remaining two expressions here, which is irrational? Nicely done. So the square root of 15 is irrational. It is somewhere on the number line, but there's no way to write it as one integer divided by another. The square root of -2, meanwhile, is not real. There's no real number you can square to get a negative number, like -2. As you'll see in a later lesson, this expression is actually an imaginary number, not a real number. So these are the two real numbers in the list. Now, if you were to add, subtract, or multiply real numbers, you'll always get a real number. Which of these two options is also correct? Does dividing one real number by another always give you a real, as long as you don't divide by 0? What about taking a root of a real number? Is that result always real? Right, taking certain roots of negative numbers can give you imaginary numbers which are not real. So this was the correct answer. Dividing one real by another will always give you a real result, as long as you're not dividing by 0, which is undefined. So there you have it. The real numbers are the set of all the numbers on the number line. So that's all the rational numbers and all the irrational numbers. Actually, a good definition for the irrationals are all the real numbers that are not rational.